Polynomials and power series today. And this is a subject I've touched on, I've mentioned in previous videos, but now I want to devote an entire video to this, talking about what we mean by polynomials and power series. And this is a formal context for the subject. Does not mean I'm going to be wearing a tuxedo. What it does mean, I'll explain in the context of an example. And according to one recent poll, in 2019, the most popular choices for babies' names in the USA were Sophie, Olivia, and Emma, that's for girls, or Liam, Jackson, and Noah for a boy. Please forgive me for using stereotyped colors for girls and boys here. I'm not trying to be binary. The choices of color here just help with the readability of my presentation. Now, anyone who has taken our combinatorics course has probably seen counting problems something like this one. The idea is pretty elementary. It's in fact much more elementary than analysis, as I'll explain shortly. And the details of this are not particularly important, just the idea how to use a series in this context. Now, in my problem, I'm trying to rank choices of name for a new baby, which hasn't been born yet, and I may or may not know the gender of the baby yet. But let's say I want a list where I rank my personal top choices of name and top choices taken from the top names in last year's poll. And my list can include any number of girls' names and boys' names as long as they add up to n. And by the way, I don't need to rank girls against boys. I just have a list that separately ranks the girls' names and the boys' names, just not ranking boys against girls. So how many ways can I come up with such a ranked list? For example, let's suppose that n is 2, and therefore I'll take either the top two girls' names, which were Sophie and Olivia, and then I can rank those two names in either order. Or if I take the top two boys' names, Liam and Jackson, then I can rank them in either order. Well, if I take the top girl's name and the top boy's name, then my list just has two names, Sophie and Liam, and I don't have to rank one against the other. Altogether, there are 5 possible ranked lists having two names. So I'll write A2 equals 5. Now let me work out also the answer for a few other values of n. I like to start for the first example with something small like 2, and then that way it's big enough to see what's happening, but not too large to get really complicated. But now let me work backwards to n equals 1. Then my list would only have one name. So choosing the top names from last year's poll, my list looks like either one name Sophie or one name Liam. That's 2 possible lists. So A1 equals 2. Now, for n equals 0, my list would have no names, and this is what that list would look like. It's an empty list. There's only one such empty list. So A0 is 1. Now let's go forwards with n equals 3. I could choose the top 3 girls' names, and I can give my personal ranking, and there are 6 ways for me to rank them. Or if I take the top 3 boys' names, there's another 6 ways there. Or my list could have 2 girls and 1 boy, or the other way around. Now altogether, I get 16 possible ranked lists, and I've shown them all here. So A3 is 16. Now I could also go further down in the 2019 rankings and see what names were popular last year, and then I can work out AN for larger and larger values of n. I could even write down a formula for AN in general. But I want to write down the answer this way that makes use of a series, because this is very convenient, especially if you have a computer. This is the way I would actually do it if I did it myself. the point is, instead of having to carry around this huge infinite sequence, an, I tie them up in one expression, a of x. And this is a power series whose coefficients are the terms of my sequence. So if I know the terms of the sequence, that gives me a of x. On the other hand, if I know what a of x is, then that gives me all the terms of the sequence. It's a convenient way to wrap them up in one object. How do I actually know what this a of x is, and what have I accomplished here? Well, it turns out we have a very nice expression for this a of x. This is where the combinatorics comes in. I won't go into the details. The explanation here is in a combinatorics course, but there we learn certain basic principles or recipes for writing down what this is. And it turns out, take my word for it, a of x is just the square of a much simpler series, which I'm calling g of x. The coefficients in g of x are just the factorials. So it's easy to generate this using software on a computer. And then I just write down the thing and square it out and get the series a of x that I wanted. Like I said, you should be really doing this on a computer using something like Maple or Mathematica, maybe Sage if you have Sage installed. And then voila, you start reading off the coefficients. Observe the first few coefficients, 1, 2, 5, 16, which was the start of our sequence. You can go as far as you like down the terms of this sequence. They grow really fast. You certainly wouldn't want to be doing this by hand, but this automated method works really well for answering our original problem. If you have a few terms in a sequence like this, you want to learn more about it, you just look it up in the online encyclopedia of integer sequences. Try it online. This one pops up really easily because it's a popular sequence, and the website lists more than 60 references to this sequence in the mathematical literature. So what's my point? Well, I just showed you how to use a power series to answer a particular problem about counting something. I never had to even think about convergence. Just because at no point did I ever use this series as a function. Never used it as a function. My computation is purely symbolic. You know how to square out the series g of x algebraically. You might call it college algebra. Certainly no calculus involved here. And you could work out the first few terms by hand if you wanted to, before they get too large. After that, just use a computer. So talking about formal power series is really just talking about power series. Forget the word formal. Forget functions. Forget convergence. Forget just about everything. Just do everything symbolically. Nothing to panic over, nothing new to learn. In fact, if you do this properly, it's about just forgetting what you learned in calculus, right? Formal power series are better called symbolic power series, or better yet, just power series. So let's take the set of all power series in X. Let's say for now with real coefficients. If I wanted to restrict to integer coefficients, like if I were doing combinatorics, then I would. But our interest now is getting into analysis, so I want to think about maybe the real numbers as coefficients. This gives me a ring R double bracket of X. Notice the double brackets here to indicate I'm talking about power series. Single brackets would give me just polynomials. Now, R double bracket X is a ring. I can add power series term by term. I can subtract them. I can multiply them out, just like I squared my g of x in my previous example. So you can see that they form a ring. If my coefficients were from some other ring in place of the reals, I would indicate that in my notation. If I do this, I really should be restricting to a commutative ring for the coefficients. Otherwise, you can't really collect terms the way you want. So in my first example, the computation a of x equals g of x squared was performed in the ring r double bracket of x, or if you prefer, in z double bracket of x, which would have been appropriate in a combinatorial setting where we're counting things and getting integer answers. Please note here that x is just a symbol. It's a placeholder. In this role, we refer to x as an indeterminate. I repeat that x is not a number here. It's just a symbol. Why? Well, because if x was actually a number, then everything becomes a function of x, and then I would have to worry about convergence. In my example, if a of x and g of x were functions, and if you were to try to plot them, their graphs would be quite trivial. Just a single point is the origin. That's the only point in the graph, because these series do not converge at any point anywhere except 0. I repeat for emphasis, in this ring, all computations should be performed at the symbolic level with x being just a symbol. And convergence never arises. I certainly don't want to think about these things as functions. That would be silly. Now, I don't deny that convergence is important in certain contexts, but not here. So if your entire world is limited to undergraduate calculus, this will come either as a bombshell or a relief, possibly. So you have two different power series, a of x and g of x. They are different series, and they represent the same function. It's the utterly trivial function with only one point in the graph, the origin. But the series are non-trivial, and they solve certain recognized counting problems. At least the a of x has over 60 references in the mathematical literature. Power series have many applications, and one of them is described in calculus, where you probably first saw them, to represent functions. Another is in combinatorics, where we often use them to answer a wide variety of counting problems. Here's an example that leads to a very different application in, I would say, electrical engineering and information theory. So start with the field of order 2, which I always denote as F2. These are going to be my coefficients for my series. So now I have the ring, power series in x with coefficients in the integers mod 2. So all the coefficients are zeros and ones. So where do such power series arise? Well, imagine that you have a web camera, which you turn on at time 0 and it starts sending out a video feed. This is an electronic stream of bits, which are zeros and ones. The entire video feed is an infinite sequence of bits, which we can encapsulate using a single expression, which we call this power series f of x. Its coefficients are just the zeros and ones in the transmission. And why would you introduce this ring structure for something like a video feed from a camera? Because we process digital information in many ways, such as compression, decompression, encryption, encoding using error-correcting codes. So these are processes all making use of algebraic operations from inside the ring. The actual addition, subtraction, and multiplication of series in the ring. The ring operations can be performed by personal computing devices using software like Maple, or they can just be done very naturally by much more basic electronic circuits like shift registers. Very, very primitive circuits can do the required arithmetic in the ring. All for very practical purposes of information processing, including basic things like preserving the quality of your video feed. And of course, besides video cameras, nowadays there's all kinds of digital information moving around by wires, optical fibers, radio transmission, etc. And we use the same basic principles in every case. I kid you not, this is big stuff. Power series with coefficients in finite fields are used in kinds of things that I work on, But my hunch is that these things actually appear more often in electrical engineering journals than in math journals. So transition now to talking about just polynomials. Once again, x is just an indeterminate symbol rather than a number. Again, this distinction can become important in a lot of contexts. If the coefficients come from a commutative ring R, then R bracket x is the set of all polynomials in x with coefficients in my chosen ring R. Once again, R is a ring. This means if you add, subtract, or multiply two polynomials, you get a polynomial in the same ring. The polynomial ring is just a subset of the ring of power series. Because if you take a power series where all the coefficients are 0 after some point, this is exactly what you have, a polynomial. The polynomials are just the power series with only finitely many non-zero terms. The polynomials are not just a subset, they are a subring of the ring of all power series in X. Now, the two rings that we have talked about are not fields. Let's focus on the polynomial ring with real coefficients, so R of X with real coefficients. If you try to divide two polynomials, you don't get a polynomial in general. Just like in the integers, if you divide two integers, you don't get an integer in general. But remember how we resolved that issue for integers. We did that in a previous video. So you construct the rationals from the integers by a formal process or symbolic process where you introduce fractions. And you can do exactly the same process to polynomials. And what that will give you then is this field of rational functions. And now you use parentheses rather than brackets to indicate rational functions. Our x with parentheses is the set of all rational functions with real coefficients. The rational functions are just formal or symbolic expressions. You write down fractions with numerator and denominator that are polynomials as long as you do not allow 0 denominators. This gives a field just like the rational numbers gives you a field. Hence the term rational function. Like rational number, rational functions are ratios of polynomials. And you can similarly do this for any field f of coefficients in place of the real numbers. Now, to really understand this as a field, you need to recognize something about how this works. Here's an example. I've multiplied two factors to get 1. The first factor, x squared minus 1 over x squared plus 3x, that's a non-zero rational function. We're in a field, so every non-zero element has to have a multiplicative inverse, right? And I've written that down as the second factor, x squared plus 3x over x squared minus 1. When you multiply these, you actually get 1. No ifs, ands, or buts here. Now, if your head is stuck in the world of functions, then in your head you're thinking, wait a minute, the first function is not defined at a couple points like 0 and negative 3. The second one is not defined at plus or minus 1. So you don't quite get 1 because you have some points where this is not defined. That's if your head is stuck in functions. We are not. We are looking at symbolic expressions, and there the reality is much simpler. This technicality does not arise for us because we're just doing symbolic expressions here. What I'm telling you can be either confusing or liberating, depending on how you have trained your mind. Certainly there's a time to think about functions, but that's not here. We certainly try to force calculus students to think about functions, and it's hard work. But then there are many situations, in particular many applications, where that's not the appropriate viewpoint. In this video, I'm talking about polynomials, rational functions, power series, all from this symbolic or formal point of view if the meaning of the word formal or symbolic is starting to get across by now. So the terms rational function and generating function are largely misnomers because we're not using functions here. Now, so far, here's the objects we have, starting with a field f for the coefficients. I have at the bottom the polynomial ring in X, then the ring of power series in X, and also the field of rational functions in X. All of these have coefficients in our chosen field, f. And then there is one thing that goes on top of this picture to complete what's going on. This is a very natural idea, but unfortunately there's not really one good standard name for it in the literature. The symbols are standard, but the names can vary depending on who you talk to. The two structures here on the left, I have to say, are rings. The ones on the right are a little bit more than rings. They're actually fields. So you can think of this new object, f double parenthesis x, as the field formed by taking quotients of the power series, the same way that we take quotients of integers to get rational numbers, and you take quotients of polynomials to get rational functions. Now we're doing the same thing with series. Take quotients of power series to get these new things, f double parenthesis x. And it turns out that there's a more direct way to write these. There are a new kind of series which allow negative exponents. But the catch is that you only allow a finite number of negative exponents on the x. That's what makes this all work. I've shown you here the definition, and the first term that I've indicated as the degree k term. This is the lowest degree term, where k can be any integer, positive, negative, or 0. And you can have infinitely many terms after that, but you only have a finite number of terms with negative exponent. So this extends the ring of power series, f double bracket x, in which we did not allow any negative exponents. Now we do allow negative exponents, allowing only a finite number of terms with negative exponent. Now let's mention the terminology. These series are Laurent series, but for some authors, a Laurent series can allow infinitely many terms with negative exponent as well. We do not. So if your understanding of Laurent series is allowing infinitely many terms in both directions, then this is a special case. Also, there's the terminology of Puiseux series, but there you actually allow fractional exponents. So once again, we're looking at a special case. And rather than wrestling with nomenclature, I'll just refer to these as Laurent series. So whatever you call them, I assure you that the concept is very natural and universal. The notation of f double parenthesis x is also standard. It's a fundamental and canonical part of the picture. In order to explain how this new field fits into our overall picture, I want to show you something about how a rational function can be expanded as a Laurent series. So for concreteness, I'm going to assume my coefficients are rational numbers. And the same explanation works regardless of your choice of the field of coefficients. Let's take this particular rational function, h of x. According to what I'm saying, this has to be able to expand as a Laurent series. Let's check this. I want to, first of all, cross-multiply to eliminate denominators, compare the lowest degree terms on both sides, and you quickly identify what the missing ak x to the k is. It would have to be half times x to the minus 1. And fill this in, and now expand stuff out and compare terms, and that would be the next term is the a0 term, and If you start solving, equating coefficients, you get a0 is 1/4. And now, again, expand stuff out and simplify. I'm omitting a bunch of this dirty work. And after expanding and comparing terms of degree 2 on both sides, we get that a1 is minus 17/8. So if you fill in that, and again expand and compare terms of degree 3 on both sides, you get a2 is 77/16. Again, fill this in and update. You can keep going as long as you want. You wouldn't want to keep doing this very long by hand, but in principle, you can find as many terms as you want if you're careful. And here, I'm going to check my answer. I'm going to use the computer. My favorite software for this purpose is Maple. I've asked for 12 terms in Maple, but I could ask for 1,200 terms. Don't do that. You can't fit them on the computer screen. But you could ask for 100 terms, and Maple will show you that pretty quickly. Or you could just ask for one particular coefficient if you only care about, the 100th term or the 1,200th term in the Laurent expansion. And then you wouldn't have to print them all, but Maple will find it. Now some comments here. It is really no harder to divide to Laurent series than it is to divide to polynomials or to power series. So formally, it's all this same process. This shows you that our set of Laurent series is a field. Moreover, it is the set of quotients of the power series. And by the way, there are many ways to get the series expansion other than the one I'm showing you here. You could, if you chose, even use the method from Calc 2, where you compute Taylor series by taking higher order derivatives and then evaluating them at 0, dividing by the appropriate factorial. But that method would be a lot more work. Trust me, the symbolic method is easier than doing it by finding derivatives. Another comment, all my infinite series are centered at 0. Because they're powers of x. They're not powers of x minus 2 or something. Both the ordinary power series and the Laurent series are all centered at 0. If you're worried about how canonical this really is, whether you would actually get the same thing if you center your series at a different point, the answer is yes, you get the same thing by a simple substitution of the indeterminate. The series centered at 0 are canonical, and they tell you everything you want to know. Again, it's a little sad that our calculus courses just give us Taylor series and leave us to work out everything the hard way, when there is typically a much easier way, algebraic methods that suffice to give you everything you want, just like I'm doing in this example here.